Ladies and gentlemen, we are going to continue our study of projectile motion by staying with the same demo apparatus from the previous lesson. Okay, you've seen this in action in class, and we also had it profiled on the previous vodcast. So the only thing I've done this time is I've actually added some numbers. Okay, so I made the demo apparatus a little bit higher. You can see over here that it's 2 meters. Okay, 2 meters high, right? It's a little taller than I am, so that's definitely bigger than the apparatus we use in class. And then I sort of arbitrarily just kind of came up with a number, a launch velocity of 5 meters per second. I can tell you that in reality it's slower than that, but I just picked a nice round number. And what we're going to do is actually use our newfound skills, okay, using the kinematics equations to actually get some answers by firing this apparatus, okay. And what we'd like to solve for here actually is we'd like to solve for the horizontal range of the marble. In other words, how far away does this marble get horizontally from its launch point? Okay, so in order to do that, I'm actually going to switch to the next page now, and we're going to work some things out. Let's go. You see on the screen, okay, I've got my smaller sketch, and I've done a step that many of you are still skipping, okay, and that is the C of skleps, right? So sketch for S. First thing is done. A lot of you are doing the sketch, but many of you are forgetting the coordinate system. Okay, the coordinate system is very important. You see my red dot here. Let me get the right color. Right, here's my red dot, and that's where my origin is going to be. You could also choose the origin to be right here. That would be just as valid. Okay, it's your choice. Okay, I'm going to go with the one that I already marked. And notice that I've also written right here, I've shown which way is positive, to the right and up. Okay? All right, let's go. A lot of these we can fill in based on the information given. Based on where my origin is, I can see that my initial x position is 0. Right, I'm lined up with the origin. I don't know my final x displacement. That is what I want to solve for, right? That's going to be my final answer. The initial velocity was given as 5 meters a second. It was all horizontal. And if you remember, there's no acceleration in the x direction, right? No push or pull in the x direction once the ball leaves the launcher, right? Once it becomes a projectile. That makes the final velocity also 5 meters per second. Okay? Now we can go to the y side and also fill in some numbers. We see that our initial y displacement is actually at 2, right? The marble starts 2 meters above the origin, and it ends at the origin, right? At the end of the problem, the ball is on the ground, which is, vertically speaking, at the origin. My initial y velocity is 0. Remember that horizontal projectiles don't have any velocity initially. I don't know my final y velocity, but I do know that because of gravity, the acceleration in the y direction is negative 9.8 meters per second squared. Your general approach to most, not all, but most projectile motion problems is that you will solve for time on one side and then take that answer and use another equation on the other side, right, on the other dimension to get your final answer. So a good thing to do here is to figure out which side is my final answer going to be on. Well, we've already talked about that our final answer is right here, right, our final x displacement. That's what we're trying to find. So if our final answer is over on the x side, that means we're probably going to start on the y side. Okay, so I'd like you to think about on the y side, which equation could you use to solve for time? At this point, I'm not covering anything new, so I'm going to pause the video, and then I'm going to work out the problem, and I'm going to challenge you to work out the problem on your own. Okay, I challenge you to pause the video now, work the problem out, and then push play again to check your answer. Okay, obviously if you get stuck, you can just keep going. But I'm going to pause the video now, work out the problem, and challenge you to do the same. Okay, you see most of the work on the screen. I started on the y side, so let's look over there. Some students might ask, Mr. G, how do you know to do equation 3? Well, we wanted to solve for time. There's only 2 equations that have time in it. And the easier one, we don't have the final velocity, right? We didn't have that one, so we couldn't use 2. That left us with 3. Plugged in the numbers, did some algebra, isolated the variable, took the square root, and I got the time. Okay? That time that is true on the y side is also true on the x side. Okay, it's the only number that's the same on both sides, both dimensions. And then if you remember, the only equation that really works on the x side is equation 3. And even then, it's a simplified version, right? When the acceleration is 0, that whole term goes away. Plug in your numbers, and you get 3.2 meters. That would be the horizontal range, how far the marble gets away from the launcher horizontally. Okay, that was really practice and review from what you learned in class. The thing that's new today that I'd like us to do is to focus on when the marble hits the ground, the instant before it hits the ground. Okay, that would be down right here. Okay, and what I want you to think about is what we want to solve for actually is how fast is the marble going when it hits the ground, and at what angle does it hit the ground. You can see by the red vector that it hits the ground at an angle. Okay, now let's look at what we know at this point. Okay, we know that when the marble hits the ground, that it still has a horizontal speed of 5.0 meters per second. Okay? Hopefully you can see that if we knew what the vertical speed was, right? If we knew what the vertical speed was, then we could do Pythagorean theorem, okay? X squared plus y squared equals c squared square root. Right? We could solve for the resultant velocity, which is that red diagonal. And that's exactly what we're going to do. Okay? But before we can do that, we need to get this y velocity. Okay, so let's do that. Let's go to a new page. All right, and you see I've reproduced right here. Okay, the instant the marble hits the ground, and we'll label what we have. We know that this y velocity is that. Okay, excuse me, the x velocity. Now we want to solve for the y velocity. We can do that pretty easily by coming over the y side and using another equation. Okay, in fact, we'll use that nifty little equation 2 that you probably like the best. All right, and we're just going to solve here. Run a little bit out of space, but I already know the time. Okay, so it's negative 9.8 times 0.64. Okay, and that's going to be to the nearest tenth, 6.3 meters per second. Okay. In other words, over here on my triangle, right, I've got that. Okay. Now I can redraw this triangle so you can see it a little bit better. Let's try that. So you can see the resultant a little bit better. Here's my 5. Okay. And then remember, I can move vectors, and I put them head to tail like that. And then I draw the resultant. Okay. So what I'm after is this resultant here. Okay. And in order to do that, I'm just going to use the Pythagorean theorem. So let's do that. Okay, you see right here that I've used the Pythagorean theorem, right? R being the diagonal, okay, being the C, if you're thinking about Pythagorean theorem. But notice what else I've done. I've drawn a big yellow arrow across the whole screen. Okay, what I want to emphasize to you is that now we're no longer working in each dimension separately. What the Pythagorean theorem basically does is it allows you to combine two one-dimensional numbers, right? In this case, we have 5.0 in the x and 6.3 in the y, and it allows us to get one two-dimensional number. So I want to emphasize that I'm no longer working in just the x or just the y. I'm combining them for a two-dimensional answer. Okay. All right. So if we plug these things in, it's just going to look like this. Okay. And got to square all that, take square root, and you're going to get a final answer here. Okay. With the same units as these, right? I forgot to add them in, but the units are going to be the same. It's going to be meters per second. And this comes out to 8.0 meters per second. Okay? In other words, the ball has sped up, as you know, from its initial velocity of 5 when it left the launcher all the way up to 8 because gravity accelerated it. Okay? So we do have a final answer that's larger than the initial velocity, which makes sense. All right. Remember that when this marble hits the ground, it hits it at an angle. So the last thing you want to be able to do is determine the direction of the marble when it hits the ground. Okay, and for that we're just going to use the old inverse tan trick. Okay, and we're going to give our angle with respect to the horizontal. If you look at this triangle up here, we're talking about this angle right there. That's the angle with respect to the horizontal. So remember to find that angle. You just see that nifty inverse tan trick. Okay. At the opposite side, 6.3, over the adjacent side, all right? And when you put that in a calculator, you get about 52 degrees, okay? So that we would then express our final answer as the net velocity, or let's use v, okay? V equals 8.0 meters per second at 52 degrees below the horizontal. That's how you would express the final answer of the velocity when the marble hits the ground.